so this will be the second part of the quantum analog experiment. So from before I showed you the frequency, so the voltage as a frequency. Now we're going to look at the frequency as a function of amplitude in voltage. For that we change the speaker input, the speaker output. We disconnected this and we send this to the DC output that you see here. We switch this guy, which is frequency to voltage converter, and so now voltage will be now we're plotting a frequency on the x-axis, but instead we're gonna see it as a voltage. So that's what it's going on here. The detector output is now going to channel 2, and so now we changed our display to XY mode. Now we don't have YT. So now what you see on the X is Y is voltage, and then we interpret that whatever is on the Y as an amplitude. Okay? And so this is a way to verify the locations of those resonances we saw before. And to verify that they are correct, how do we check them is, like I said, we look at the locations at which the amplitude is amplified. And so for example here, now, let me move this out of the way. So what I have done here is set the display to XY mode and they persist. So any movement that I do of this, any movement in the signal will be tracked, will leave a trace. And so you can visualize the presence of a resonance like you saw there. Let's go further in frequency. There's another one, and if we go further, we might be able to see another one. And so that goes with the idea that, as you see here, that's quantum, the principle quantum, everything's quantized. And so you see that resonances do not happen at any random location. They have their predefined locations, which is based on the length of the tube we have here. If we change the length of it, of course, the frequencies at which resonances occur will change. But this is another way to visualize, to see actually what's going on. Okay, so that will conclude the experimental setup for the quantum analogs experiment.